in recent years, economic decision-making has become more and more mathematically oriented. Faced with huge masses of statistical data, depending on hundreds and even thousands of different variables, business analysts and economists have turned to mathematical methods to describe things that are happening, to predict the effect of various alternatives, and also to choose a reasonable course of action from the many, many different options that there are. And calculus, believe it or not, is one of these options. And we are exploring how using derivatives can help businesses make decisions. And that's part of what optimization is doing. Now, a very basic formula for revenue could simply be this formula, that revenue, or R of X, is equal to XP, where X is the number of units sold and P is the price. Now, hopefully this makes sense and even seems a little bit high schoolish in its simplicity, but it's also true in the business world, that the number of units that you sell at a particular price will give you your revenue. Now, if a business is small and it's in competition with other companies, its sales have some effect on the market price of whatever it is they're selling, how much it costs overall, but it doesn't have as much effect as a larger company. And of course, if a company would have a monopoly on a product, that means they're the only ones producing it, well then their sales greatly affect the market price. Their sales would be the market price. And if this is the case, even if you're a monopolist, and when I say a monopolist, I'm using that as a term that the book will use, and that simply means that you can set the price for what you need it to be, what you want it to be, and that will be an acceptable market price. Now, realistically, usually it's the larger companies that can act like this, and the smaller companies are affected more drastically, but it's possible for small businesses to also affect the market price. And in fact, a small business can even become like a monopolist if it meets certain criteria or finds itself in certain situations. A smaller company, if it has a faithful customer base, it can act like an almost monopoly. You can charge whatever it is if you know that your customers are going to buy whatever it is you produce, regardless of the cost. This would be an extremely loyal customer base. And kind of think of it as, you could say in a joking way, that you know your mom will always buy from you, kind of thing. And now, if you can have several customers like that for some reason they're just going to be faithful for whatever reason, then you can set your prices higher and people will those customers will still pay. Now, you can also have an almost monopoly if you offer a unique product or offering. Say you are the only restaurant in town that prepares Caribbean food. Well, you can set your price for whatever you want. There's no other Caribbean food restaurants that I'm aware of in Klaipeda. So if you set one up in Klaipeda, you set your price. It affects the market price because you're the only one, even if you're small. And of course, the third way that you could have an almost monopoly is if you have product superiority. If you simply make a product that's going to last 3 or 4 times longer, perform 3 or 4 times better than anything else in the market, you can set pretty much the price you want within reason, and people will buy it. After all, if I knew that something I bought from your company was going to last 10 years, and for everybody else it would last only 3 or 4 years, well, I'd be willing to pay 2 to 3 times the amount to buy it once, and probably pay less than if I buy 3 things or 3 products from your competition, because I know in 3 years their price is going to go up again, and then it'll go up again in another 3 years. And it would be cheaper to buy yours once now and have it last for 10 years. So you can charge a little bit more, even up to a lot more, and still survive and continue as a company. So these are some ways that a small business can have an almost monopoly. But in today's world, there's not that many companies that have a true monopoly. Now, even if you are a monopolist, customers will buy a large amount of a product or service when the price is low. Now, we know that that's true. If we keep our, get the board working here again, if we keep our formula here that revenue, or R of X, is equal to XP. If we look at a typical demand curve, an average or a typical demand curve looks like this blue curve. And when we look at this, we realize that when demand is high, when you're high in this blue line, then a higher price can be charged for the product. But when the price is low, when the demand is low, then the price needs to be low. You can only charge a lesser amount. So again, the demand curve, when demand is high, it's up here, and you can charge a higher price. And when demand is low, then you can only charge a lower price. You'll get more of this when you study economics in future semesters, and it's a typical curve. You'll learn a lot more about it than I'm going to teach you right now. And we realize that price and demand are directly related. If we think about it, if we know this is the demand curve, but if we pretend that it wasn't here, we could come out and say, well, you know, I have a product, and if I charge a high price, I'm not going to sell as many of the item if I charge a higher price for this one particular product. So if that's the case, if I'm going to set a higher price, I may only sell, I may only sell a couple of things. A high price means a lower quantity that I will sell. Now, if I set my price lower, if I set it really low, well, then I'm going to sell a great quantity if it's out here. The price is low, the quantity is low. If I set a price that's in a median price, or a medium price, in between the two, well, then the quantity is going to also be between the two. Well, so if I was going to graph this, I would get a whole bunch of dots in this basic same shape as this particular curve. So we begin to realize, well, yeah, if we set our price, or our quantity, if we set our price, it will affect our quantity, but that's also the demand curve. So we realize that the two things are actually the same thing. Our demand is our function. If this blue line is the demand, they call it here lowercase p for demand, just what they do. It equals some function. And yet if we look at the price, a high price means lower quantity that we sell. A lower price means a higher quantity that we sell. So it follows on the same curve. So the demand equals this function. And so we could actually do a substitution in for this. That, oops, there we're having a little bit of trouble with the PowerPoint here. There. So if the price can be substituted by this function, we could say that it's f of x. And then the p actually develops two definitions. That this xp, we said it was price, quantity times the price. But it can also be the quantity times the demand. So this is literally saying that the demand and the price is the same thing. So when we see this formula, R equals XP, realize that it's X times the price, and it's also at the same time X times the demand. This will be very handy when we work to solve problems. We'll first use it, we'll figure out the price, we'll figure out the demand, and since demand is the same thing as price, when we've calculated our revenue from the demand, then we can go back and know what price we should set things for. We'll see this very shortly. Now, here's a particular problem that's in the book, and it kind of explains straight line demand and revenue. The problem is a swimming club offers memberships at a rate of $200, assuming that a minimum of 100 people will join. Now, for each member in excess of 100, the membership will be reduced by $1 per person for every member. So if 100 people join the club, the membership for each person will be $200. But if 101 people join, then they're going to drop the membership rate to $199 for every person. So it's not that they're going to charge $200 for the first 100 and then drop the price for everyone after that. everyone's fee is going to be reduced. So in order to figure out how much they should charge, they want to use demand as part of this. And that's what we're going to see in a minute. So here, at most, 160 memberships will be sold. Maybe it's the size of their facility. They can only house up to 160 members, and then it's too crowded. So how many memberships should the club try to sell in order to maximize its revenue? Well, so far, we know that we have a point here where if 100 people join, it's going to be $200 per membership. And we know that we're going to have at most 160 members join, and we could calculate what that rate would be if all 160 would join, but we want to maximize the revenue. When we're doing this, we're trying to find the value of X that will maximize the revenue. So we have to have a revenue function. And of course, to do this, we must first create our demand function, our P, or our f of X. Well, if we think about this, we know that we're guaranteed to have 100 people in membership. I guess that's actually in the problem I didn't copy into the book. They're confident they're going to have at least 100 members. So we're going to not worry about situations where X is less than 100, only when X is from 100 to 160. Now, if we start with 100 members, for every one more member that comes, the membership price will fall by $1 for every person who comes. So as X goes from 100 to 101, an increase of 1, the price will fall by 1 unit, from 200 to 199. We realized that if we were going to try to graph this, that if we have 100 members, we're going to charge, say, 200 liters. Here would be 100, and here would be, $200, not liters. Well, this is going to be a little bit not to scale because my space is limited here. But if we have 101 members, the next one out here, the price is going to fall and go down. If we have 2 more members, or 102 members, it's going to continue to go down. And we realize that it's falling at a rate, it's going to go down 1 unit for $1 for every member that you do. Well, then from that we can calculate the slope. If we're going down, our slope will be the change in y over the change in x. And we know that the line is going down, so it's going to be negative, and the change in y is 1. It goes down $1 for every member you get above 100. So the slope, that's a little hard to see, but it's going to be -1 with this. Well, if this is the case, the slope is -1, if we could figure out where it crosses the y-axis, we could use y equals mx plus b, and we could interpolate where that would be, figure it out. But we could also just simply use the point slope formula, the y minus y sub 1 equals x, or excuse me, m times x minus x sub 1, where we have the slope already, and we have a point on here at 100 and 200. So now we have a point. So using this in the equation, we can say y minus our y value of 200 equals our slope of -1 times x minus our x value of 100. So this is y minus 200 equals minus x plus 100, or y is equal to minus x plus 300. So now we have our function, our f of x. So we can say that this is the f of x that we're looking for is simply minus x plus 300. So that was looking at it somewhat logically. We say, well, I didn't quite see that way. Well, maybe working at it this way could be helpful. We know that when we have 100 memberships, the price is going to be $200. Now, if we go to our maximum membership, we can realistically pick any point, but if we go to our maximum membership, that's when we have 160 members. 60 members above 100. And that's what this is saying here. If we have 60 members above 100, then we're going to lower our price by the same number, by $60. So it's 200 minus 60, that's 140. Now we have 2 points on the same line. That the original point of 100 and 200, and now 160 members, $140. So we can determine the slope using these 2 points. We calculate here, we use y sub 2 over y sub 1 minus x sub 2 minus, or excuse me, x sub 2 minus x sub 1, and we calculate that to be minus 1. And then we use the point slope form, just like we did before. We could pick either point, but for the PowerPoint here, I chose, again, the first one. So we choose y minus 200 equals minus 1 times x minus 100, and that's just like what I did before. And we're going to get y equals minus x plus 300. So now this is our demand equation. Whenever we're calculating this y, or f of x, it is the demand, small p. Now, all that just to get the demand function. To find our revenue, we know that it's x times p, x times the demand. So it's going to be x times our p, which we just calculated as minus x plus 300. Multiply this together and we get minus x squared plus 300. Now, we want to maximize our revenue. So we know that we need to take the first derivative, set it equal to 0, and solve for x. So, our revenue function, find the first derivative, it's minus 2x plus 300, and then set it equal to 0 and solve for x. We find that it's when we have 150 members. So, when our goal should be to try to sell 150 memberships, because of the demand, we know that it's very likely, and in fact it should happen, that if we have 150 members, we should reduce our price. For every member over 100, we reduce our price by that same amount. If we have 50 members over 100, we're going to reduce our price from 200 by 50 down to 150. This should mean that we should get 150 members if we set the price at $150. And we can look at this and realize that this is the demand curve. We could graph it and say, yeah, we should get a maximum revenue. If we set the price at $150, we should get 150 members and have maximum revenue. Now, when we're working with trying to find maximum profit, there's a little tip I can give you. We know that profit is equal to the revenue minus the cost, and then we can calculate the marginal profit from that. We know if we're going to try and find our maximum profit, we set the p prime, the first derivative, or the marginal profit equal to 0 and solve for x. And that will tell us where our maximum profit will be. But we also know that we can calculate p prime in 2 ways. We can do like we just simply said, calculate our profit, and then by taking revenue and subtracting the cost, find the formula, and then take the derivative of that to find the marginal profit. But we could also realize that the marginal profit is going to be the marginal revenue minus the marginal cost. Either of these formulas would work. We get p prime, we set it equal to 0 and solve. We realize, again, that we will find the maximum profit will be when p prime is equal to 0. But if p prime equals r prime minus c prime, and that equals 0, well, if we look just at this part and ignore the p prime, say that the marginal revenue minus marginal cost equals 0, then it's going to also be true that your profit will be maximized when r prime equals c prime. After all, if r prime minus c prime equals 0, you can add c prime to both sides, and we get r prime equals c prime. So this can be a shortcut. It saves the step. This only works when maximizing profit. It doesn't work for average profit or anything else, just when maximizing profit. You can jump straight to here, r prime equals c prime, and you don't have to calculate what p is and then calculate p prime. You don't have to do this step and the p prime equals r prime minus c prime equals 0 and then go from there. You can just start here. It doesn't save a lot of time, but it saves a couple steps. It can be nice. Now, in working with profit, here's another problem. The demand for a model of telephone is, the demand is equal to 512 minus 100x. And the cost in litas of producing x thousand telephones is our cost function here. Find the level of production and corresponding price that will maximize profit. Well, we know, if we're working with this, that we really want to go in and to calculate what our marginal revenue is, a marginal cost, is that we need that to calculate maximum profit. We want to take the marginal profit, set it equal to 0, and solve for x, and that will give us our answer. But in order to find that, we need to have our marginal revenue. To have that, we have to have a revenue function, and we're not given it here. So, how do we calculate that? Well, we remember the simple fact that our revenue, our R of x, is going to be equal to x times p, and we are given p. So we need to memorize this one simple formula, R equals xp, and p in this case is the demand, so it's going to be 512 minus 100x. Well, of course, we want to work with this and say this is going to be 512x minus 100x squared. Now, we can make a little shortcut here. We can use this, but if we use the tip that we just learned, we know that maximum profit is when r prime equals c prime. We have our revenue function right here. So if we take the derivative of this, we end up getting that r is equal to 512 minus 200x. And now we need to use find our c prime. Well, c prime comes from our cost function. We take the derivative of our cost function, and when we do that, we realize we get simply 112. Now, we solve for x. If we bring the 112 over, we end up with 512 minus 112, or 400. If we take the 200x over the other side, or add 200x to both sides, equals 200x. Well, our x is going to be equal to 2. Now, does that mean we should produce 2 telephones? Well, no, because we were told that x is in thousands of telephones. So this realistically means that we want to produce or make 2,000 telephones. Oops, that's going to delete it, so I'll just stop there. So we need to produce or make 2,000 telephones. The second part of the question said, all right, once you figure out the level of production, and that's what we just calculated, what is the corresponding price? You say, well, we don't know anything about the price. How do we figure that out? Well, we remember that price and demand are interchangeable, that this P stands for both price and demand. So we can use this formula, the one that we used for demand, we can also use it for price. That seems a little bit strange, but it actually works because they are the same thing. Our price is going to be the same as the demand, which is going to be 512 minus 100x. So in this case, we want to do a P of 2 because x is equal to 2, 2,000 telephones. X stays in thousands, so we don't do a P of 2,000, we do a P of 2. So that's going to be 512 minus 100 times 2, which is 200. So we'd say that the price should be 312, and we were working in litas. Yeah, just straight liters, not thousands of liters. That makes sense. A 312 liter phone is the reasonable price for a phone. If it was in thousands, it would be 312,000 liters for a phone. That would not be a good thing. But we come back to this and we realize that we should produce 2,000 telephones and we should sell them for 312 liters, and that will give us our maximum profit. So this kind of thing you'll see in the homework. And remember the tip, it simply saves a couple of steps. The homework is this. Note that the answer in the back of your book for number 11 is incorrect, and I have here what the answer should be. I also mentioned it because the solutions manual is also wrong. So even if you go and check the solutions manual, it's not helpful to find the correct answer. The setup is correct. They just are using a problem from a prior edition of the book, and they've changed it in this edition. So the answer comes out to be different, even though the work's done the same way. So we'll see you in class. Have a good day.